Hello 535, this is Dr. Keith Schubert. Today we're going to be, or in this video I should more properly say, we're going to be talking about norms and how they work. Now, to kind of get an idea of norms and how they work, I'm going to consider a two-dimensional space for the moment, and we'll just try some things out in it. Let's say, for instance, I am currently right here at the origin, and I want to go over to some spot located right over here. I want to know how far that distance is. Now, to be able to measure a distance, you gotta say, how do I have to measure? Now, most of us measure this way. We just take the shortest route possible. Everybody says, well, of course, that's the most obvious thing to do. Okay, wonderful. Then what's that distance? Well, we often use, to get this one, the Pythagorean theorem. We take the number of distance on here, well, it's 1, 2, 3, and it's up 1, 2. So we say 3 squared plus 2 squared has to be equal to, and 3 squared is 9, and 2 squared is 4. Right, so that gives us that this is 13. So this side over here has to be the square root of 13. And we go, yay, we've got our answer, and that's a reasonable distance. We often call that the Euclidean distance because this is how Euclid measured things. But is it the only way to measure? And this may seem kind of a silly question to ask because most people think, well, of course, that's the most logical way to go. And they think there's no physical situation that does otherwise. But imagine I'm in a large city, and usually the example is like Manhattan, and these shaded in blocks I'm drawing are buildings. Now, I start here on this corner, and I want to reach this corner. I can't just walk through the middle of the buildings. How many blocks do I have to walk? Well, I have to walk 1, 2, 3, 4, 5. Well, you say, well, maybe that's not the best route. What if I walked 1, 2, 3, 4, 5? You can try this as many ways as you want. Doing this, you're going to end up getting 5 as your shortest distance. You could, of course, make this longer. I mean, I could take the grand tour of Manhattan, I suppose, and go out of my way, in which case I'm going to get greater than 5. But the smallest distance I can go without cutting through a building is going to be 5 blocks. Now, what is that in terms of our previous problem? Well, if you notice, 1, 2, 3, 1, 2. If you interpret these as blocks, that's exactly what I drew. So, instead of being the square root of 13 as my answer, which is kind of your classic, as we said, Euclidean, or, what you measure in your geometry classes and that, what we're now getting is we added the absolute value of 3, just so I can say it doesn't matter direction, because you could call that positive or you could call that negative. So I just say I don't care, which way you want to call your directionality, I just want the distance. And same thing with my up-down or north-south direction. I don't care which way you are calling the measurements as, I just want that distance, and you add it up and you find that the answer is 5. Now, this is another very legitimate way to calculate things. And we could say, hey, that's great. Now I've got a second way that really just kind of matters to me. Situations of, I count that outer distance. How much am I actually going to have to travel on here? Other things that might matter to you. There's another norm that we use quite frequently. To motivate it, though, I kind of can consider it the worst case dimension or something, but the best way to see it is actually understanding a little bit about this process of what we do. Now, I could say without loss of generality that I took the absolute value of each of these numbers before I squared it. If I were to write this formula up and I were to say, 3 was one dimension of my vector and 2 was the other, and I call this my x and my y direction. what have I actually done here? Well, what I've done is I've got x sub I absolute value squared, and I've summed it up for all the I. That's what this is. And then I took it and I square rooted. Okay, so that gives me one way that I could do things. How about over here? Well, this one I could treat as the sum. Again, I'm adding up all the components from here, except all I'm doing is absolute value of xi. Now if we want to, we could say we raised this to the 1, and we took the 1th root. This is implicitly the square root. Now what's a 1th root? Well, all that does is it takes the positive part of the number, but I already have only positive numbers because I'm adding positives up, so it really actually effectively does nothing other than to make these two look exactly the same in their patterning. So much so that I can actually kind of generalize this and say, the two ways that I've thought of doing measurements so far have really used something that looks like this. I've got some, actually, usually we do P here. And we'll take our summation over I of the components xi of our vectors, and we raise it to the pth power, and then we take the pth root. And we call this a p norm. Right? And we write this way of x, where we're calling this our original x, the entire vector. We don't use a single one because we already are using single ones either on scalars for absolute value or in matrices we use it for determinants. And to mention that we're saying the pth norm, we use a little p down here. What that means is this one here is therefore p is equal to 1, so we call that the 1 norm. And in particular, this one over here is a very common one used for us, and it is the 2 norm because it's 2. Now I say, okay, great, you see, I've got p. Nice forms of this. 1 and 2 obviously are very nice. Turns out it's not particularly useful for the other things. There's no good closed form solution to grab and stuff. But there is a special case here that becomes very nice to calculate. Consider the following. Take the limit as p goes to infinity of this p norm. Now, I need to kind of buy myself a little space here. When we do that, taking this limit as p goes to infinity, consider a couple little simple cases to kind of motivate the answer to this. If you remember your calculus, I can just tell you it's the largest absolute value, largest magnitude. But why is that the case? What I'm going to do, since it's calculus's job to prove it, it's my job to motivate it. I'm just going to motivate this. So imagine we take a number, let's say 1, right? And I'll take another number really close by, 2. What we want to do is we're going to take each of these and we're going to take powers of them. So we're going to have them squared, and we're going to cube them, right? And we'll do a couple different ones. Let's say, let's take it out to the 10th power. Right? So, and then we will do the summation. Now, when we square these two, we'll get 1 and we will get 4. Now the summation, right, so we'll consider this to the first power. When I sum them, I get 3. I sum here, I get 5. When I cube, I get 1, and 2 cubed is 8, so I get 9. By the time I go to 10, 1 to the 10th is 1. Okay, I almost wrote silliness there. And 2 to the 10th is 10 24, or what we call a k, inside, and so that means the summation is 1025. Now if you look at this, if I were to then come back and take, the square root of this, right, it's going to be just slightly above 2. If I take the cube root of this, it's going to be even closer to 2. And as you keep taking them, it's going to get closer and closer and closer as it goes on. Now, in order to make this kind of a little more clear, let me actually just take these roots here. So I've got conveniently off to the side, you can hear me typing. Haven't done this in advance for you, so we are live. So we'll do square root of 5, and we get 2.2360668, blah blah blah. Right, kind of ugly as that goes on after there. And then what we're going to want to do is take the cube root of our next one that's in here, and I'm using, if you're just interested, I'm using MATLAB, which I've used many times before in other ones, and we'll see. We want the cube root of 9, so I want 9 raised to the 1/3 power, and I get 2.0800838. So if you notice, I'm getting closer and closer towards 2. What happens when I have the 10th root? So I want 1025 raised to the 0.1. And now I've got 2.0001952. Dot dot dot. All these. There's more digits past there. I'm just writing enough to give you the idea of what's going on here. Now, if I kept following this, it's never going to get smaller than 2, the largest element, and it's getting closer and closer to 2, as you notice, which is really pointing out the fact that as you take higher and higher powers, the big term, whatever's the largest in magnitude, notice it wouldn't matter if 2 had been negative because we're taking absolute values, but the largest magnitude dominates. Now, that essentially means that as I run this towards infinity, all you're going to be left with is the largest term. So this does not prove it, but this certainly motivates it. All you have to do is actually take that limit and go through there. But this is not what my main interest or concern is, because my job is to teach you enough numerics that you can do a good job here, and for our purposes, being able to test problems reasonably is actually pretty important. So we've now seen we've got several different problems that are of interest to us. We've got the one, or norm measurements, that are of interest to us. We have the one norm, which is the sum of the absolute value of each of the components. We've got the 2 norm, which is equal to the square root of the sum of the components squared. This is kind of your standard Euclidean distance. And now we have another one, which is the infinity norm, and that one is equal to the largest over all the I of the absolute values of x sub I. This is kind of the biggest distance you have to walk. And this is kind of actually useful to get approximations and other types of things. What you're saying is, hey look, if I had to walk from here where I'm at right now to New York City and then 2 blocks over, really the 2 blocks over isn't going to mean that much compared to the rest of the trip I have to make from the general Los Angeles area. So the 3,000 miles would swamp the 2 blocks. And therefore the infinity norm is a pretty good approximation. Trying to add something onto that distance would be kind of kind of unimportant and also subject to errors. And this is kind of an important feature also of this. We've shown floating point numbers only have so much precision when they're holding them. The infinity norm is actually pretty good for handling robustness issues because it doesn't allow you to lose precision going on by some type of a strange round-off error or other types of things. So since you could obviously represent that largest one, you can get a legitimate measure, and it will fit nicely in memory and will give you a nice norm with all the good properties of norms, which are reasonable measures. There's an implication of this. Notice that max as a function is actually a norm-bearing operation. Min is not. So when you see and people take a bunch of samples and they take the minimum, what they have done is probably lovely for their some things, but it is not actually a norm. And so most systems that go out there and actually measure times and things like that inside your computer actually usually take a bunch of samples and then take the minimum. This is actually not a norm, it's not a metric, and therefore it's going to run into some important problems when you start trying to use it to analyze it in math. What they should do is they should take a bunch of samples and take the worst time and report the worst time your system did, because that is actually now something you can legitimately compare and show has some value. In any case, this gives you an idea of some of the basic norms that we use for vectors. Now what happens when we go up to matrices? When we go to matrices, the question is, how do I extend these? Well, there's a couple different ones that are out there. The most common one we will use is, again, an extension of the 2 norm. And how we're going to do this, the norm that we've defined so far works for a vector. Well, let's consider I have a matrix A. And what I can do is I can find a suitably compatible vector, let's say x. Right, so therefore if A is a real matrix that's m by n, to be compatible to multiply on this side, x has to be a real vector of size n, so that their inner dimension, the number of rows here, is equal to the columns in A. Let's assume that I have that. When I multiply A times x, I will get a vector again, and that vector will be appropriately sized. It's 1 by m, and so this can now have a 2 norm measure. And it's important to note, right, that A times x is an element of this m-dimensional space, or an m tuple. Now, if x were particularly large, I could arbitrarily scale this and I could throw my measurement off. So I've got to remove the effect of having put x in here. 2 ways you can do it. Most common way we usually express, we just say, find out however big it is in the 2 norm sense and divide it out. That's reasonable, gets rid of it, pretty nice. The other common way that you will see that we're going to handle this is we could have just specified that x has length 1. Now if x has length 1 under this definition, I'm dividing by 1, and therefore I would just bring you back to that nice simple state. So some people prefer to specify it that way. And what we're going to want for the 2 norm on here, remember we don't want to minimize things, so we just say which one gives me my biggest result on here. So I'm going to maximize over all the x's, and that will give me my legitimate norm. So this is probably the most common way that we do this. This is the extension of the p norms. You can actually extend any p norm you want in here. The 1 norm and the infinity norm actually kind of become interesting on their own. They become biggest row and column sum as they go through. Not really worth going into a big discussion on them. I just mentioned that as a result here. There's also another one that kind of vies for this title of 2 norm in a sense, which is called the Frobenius norm, where I just take all the elements in the matrix A, square them, and add them up. And that turns out to have some nifty properties as well. But this one is extremely useful to us. The definition is nice and simple. and it's useful to actually calculate on. So that gives you kind of a rundown. This is actually how I'm going to treat it through most of the course, because it's sufficient for what we have to do, and this is a first introduction. So I hope this helps a little bit. I guess one last thing we could actually mention on here, if I were to take, let's just go back to our norm of a vector. If I were to square this as it goes on. Now remember what we're doing on this. The 2 norm itself was the square root of the sum over I of the xi squareds. And then if I square a square root, I just end up with the sum of the squares. But the sum of the squares, I can get that. That's the definition of the inner product of x transpose times x. And so this result right here, that the 2 norm squared is equal to x transpose times x, is a nice way to go from kind of this norm notation into a kind of regular matrix or vector multiplication notation. So if you actually want to then just express the 2 norm, you could then just say it's the square root of x transpose x. That's a scalar, it's perfectly well defined and understandable, so away you go. So that's one other kind of interesting result that we do use quite a bit of the time, so worth kind of underscoring here. Hope this helps. Look forward to seeing you in class. Bye.